The topic for today is how to verify Schnorr signatures in 3000 gas. Now, to fully comprehend why it's important and how it's done, there is a lot of legwork that needs to be done. So I give you an overview why it's interesting and important. Then I tell you a little bit about prime fields and elliptic curves. I asked the question a moment before, how many of you know what it is? So it seems it's worth talking about it one more time. And then we're gonna talk about digital signatures, in particular about digital signature algorithm, which is used in Ethereum. And then we talk about Schnorr algorithm, which is very similar to DSA, yet a little bit different. And then we show you a trick how to verify one with the other. Now, the reason why it is interesting trick is that Ethereum uses DSA. And you can very cheaply verify DSA for 3000 gas roughly, while you cannot verify Schnorr. Schnorr has some interesting properties that DSA doesn't have, hence it is interesting and attractive to have it verified on Ethereum at the same price. Good. So, without further ado, first I want to talk about elliptic curves. So, what is elliptic curve? Well, elliptic curve is a set of points defined by an equation, kind of like a function, but function have just one y value for given x. There is no such a constraint in case of elliptic curves. And this is the equation, the general equation, y transform, y squared equals x cubed plus ax plus b for some a and b. Now, it's worth mentioning there is a bunch of other forms of equations, but we're gonna save it for another time. And we're gonna focus on just one equation today, on what's called SECP256K1 equation, which is used by the very standard I just mentioned, and A equals 0 and B equals 7 for that specific variant of the equation. Why the name and everything, I'm gonna explain in a moment. One technical note, so I'm gonna use animation. So I have a YouTube channel called zkWarsaw where I explain things about cryptography. And so I'm gonna use, in the first part of presentation, I'm gonna use a video I recorded for this specific, for the first video I used there. And for the second part of presentation, a video that I started working on that I intend to put in the future on the channel. Good. So this is how elliptic curve looks like on a real plane, right? And I'm gonna skip a lot of building intuition. So if you go and watch the video on the channel, there's gonna be a lot of working with with elliptic curves built on real numbers to build up some intuitions for discrete elliptic curves. I'm gonna skip it for the presentation today because it would take too much time. What I'm gonna do is I'm gonna skip all the way through. So this is like building intuitions, building intuitions, building intuitions. I'm gonna skip all the way through to prime fields because prime fields are important. If you don't, prime fields are easy, but important to understand because without that, it's gonna be really difficult to explain elliptic curves, discrete elliptic curves. Let me just push it a little bit more further. Yeah. So I apologize, the scrolling is not perfect in the video. Okay, so this is the clock. So probably anyone who had any background in computer science or mathematics knows what a modular arithmetic is. So a clock is modular arithmetic modulo 12, right? Well, actually, it's almost modulo, right? So if we move through the 12, it's gonna go and start from the beginning, right? If we keep adding to, I'm gonna maybe push it a little bit backwards. Gonna start slow, it's gonna accelerate later. If we add 2 to 11, we're gonna end up on 1, right? So this is modular arithmetics, except in modular arithmetics, we don't use numbers from 1 to 12. We use numbers from 0 to 11, 12 numbers in total, right? And what we're gonna be interested in is prime fields. So prime fields is kind of like, so it's mathematically a very different thing, but intuitively you can think about it as a modular arithmetic modular big, well, modular prime number. In cryptography, it's gonna be a big prime number, right? So in this case, we have a arithmetic modulo 13. So 13 numbers from 0 to 12, right? And yeah, the main difference between the important things about prime fields, it's a field, right? So you can add things together, you can multiply things by something else, and so on, right? So we say this is the prime field of order 12, 13 elements. And yeah, and as I mentioned, it's going to be really big prime field that we're going to use in cryptography. So usual number is something close to 2 to the power of 256, which I'm sure you know is like more than atoms in the universe times nanoseconds from the Big Bang. But in our examples, we're going to use 41 to make it visual and easy to understand. And we're going to use, for the prime fields, we're going to use a straight line. We're going to use an axis, if you will. And yeah, if you were to implement a prime field, and you know a little bit of Python, it's pretty simple. You just need to have two numbers, the value of the prime field, and anywhere between 0 and 40 in case of prime field of order 41. And you need the order, so you kind of know, in our case 41, so you know what your modulo is, right? And if you want to create one, I think I have an animation follower of that. So if you want to create one, you simply need a constructor. Constructor takes two values, value and order. And, and not forgetting, those numbers are really big, right? So in Python, we can just say integer, but almost in any other language, we would need a special big number library. Because Python integers are big numbers by default, right? And if you want to construct one, it's very simple. We just pass value and order, and we initialize an instance, right? And if we were to equal or add or subtract or multiply or do something else with the prime fields, first thing we want to say, check see if the order is the same, because it doesn't really make sense to make operations of prime fields of two different orders. And then if you want to add, subtract, multiply values, all we need to do is, first, if you want to equal, we just make sure that orders are equal and values are equal, right? But if we want to add, subtract, or multiply, we just multiply one by another, or add or subtract, modulo the prime field order, right? Sounds easy? Yeah. All right, good. And there is also inversion operation. You can think about inversion as putting something to the power of -1, or division by something, right? It is a little bit more complex, so we're gonna skip it for today. But it basically, what is important about inversion though, it gives you the result in the prime field. Inversion always exists, and it gives you another number in the prime field that if you multiply by, it's gonna give you the result that makes sense, right? So if you multiply if you divide A times B, or divide A divided by B equals C, then C times B equals A, right? But that's a little bit counterintuitive the first time you feel it, the first time you encounter it, that this number is also a number in the prime field. There is no fractions, there is no negative numbers, and so on, right? So, but I'm guessing prime fields are not very difficult to understand. Now, discrete elliptic curves are the ones that we are using in the actual cryptography, and this is how it looks like. This is how it looks like for elliptic curves, SCCP 256K1 on prime field 41, and you can see there is a prime field and x-axis, and there is a prime field and y-axis as well. Okay. And we're gonna note some things here. Well, first it's dots. It's not continuous anymore because it's discrete. It's defined on prime field. But there is a symmetry. If you see there is a blue line, and you can see the top and bottom is mirrored against the middle line, right? And there is this interesting thing. The number of the dots is close to the number of the elements in the prime field, but not equal in general case, right? So in our case, there's 41 numbers on the x and y axis in the prime field, but 42 in the group. We call it the group. The points we call the group, okay? But that includes point in infinity, and I will explain in a moment what the point in the infinity is. But what is important...
So what do you mean by in the group?
The group is just the points. The group is the points. And the prime field is here, right? So there are two different... That's gonna be weird. We're gonna have two different arithmetics, like you're used to doing real numbers and adding 2 to 5 and so on, right? Now we have a new arithmetic, modular arithmetic on prime fields, modulo 41, but we also have yet another arithmetic on the group of points. But this arithmetic doesn't have this division and multiplication. Well, it does have multiplication, but a different kind of multiplication, right? So it only has addition. So if you remember, if you did computer science or mathematics, there is a group theory, there is a field theory, and group is something that you can add, and there's certain rules about groups, and there's field that you can add and multiply, right? And group has a neutral element and a bunch of other properties, right? What is really important to kind of get into your bones, so you understand the later part, is there are two different things. There's a prime field, there's the thing on the axis, and then you can add and multiply and divide and do all the arithmetics of field, pretty much like real numbers. And there is group, which is basically a point which you can add, but you can't, for example, divide. The two are similar size, so we call the order of the group is close to the order of the prime field, right? But not equal, and in fact, there is a law that says they differ not more than a square root of prime field order, right? So, but that's something you don't need to know if you just want to use that stuff or implement or get some intuitions, right? Which leads to some interesting properties and nuances, right? Good. So on that group of points, we're gonna define operations. And the first operation we're gonna define is gonna be a negation, right? So creating new arithmetics. I'm waiting for the horizontal line to show up. Can you see a horizontal line? Badly. There is a line there. The screen is not very gentle with us today. I'll try to, yes. Here's what I'm gonna do. I'm gonna turn the lights off and maybe you're gonna see it. Can you see the line now?
Oh, yeah.
So that's the line, right? So for roughly half of the axis on the prime field, roughly for half of them, there's gonna be a point. And there's gonna, for every single x, there's gonna be 0, 1, or 2 points. They're never gonna be more than 2. And for vast majority, it's gonna be 2. And in fact, for big prime fields, it's pretty impossible to find one. But to randomly pick one, to pick the x that has just 1 point. But for now, I'm just telling you, hey, there is 2 points here, right? There's nothing on the next x, but there are 2 here, right? And they're kind of symmetrical. Right? And then if we animate further, you can see roughly, in our case there is 1, usually there is just a few point that is on the y coordinate equals 0, which means there is no twin. For every other one we have a twin, right? So the negation operation is an operation that basically allows you to find a twin, right? So here we go. Yeah, no, oh yeah, no, right? So, see, that's the point A. We use the symmetry axis, and the minus A is just the other point, right? So we say the minus from the point is simply the same point, but with the y coordinate negated, right? And because we're in the prime field, the y-axis is a prime field, that means that this A is symmetric, right? This is where it comes from. The symmetry comes from the fact that we're using a prime field. And if we were to implement prime...
The symmetry is imperfect.
Come again?
This is the one point. The symmetry is not perfect.
Yeah. There is this, but still, but probabilistically, it's you don't care about it probabilistically. Okay, so if we were to implement the point, we could use just x and y coordinate. We're gonna use field element that we implement in the previous slides. And to negate it, we're simply gonna create a new point with the same x coordinate but y coordinate negated. Pretty trivial, isn't it? Yeah. Okay, so here comes the first non-trivial thing. And to understand to understand that part, it's gonna be if that's gonna be difficult for you to understand, I think the best way is to watch the video, because there is a whole 6-minute parts of building intuitions why addition is so weird. So what we're gonna do now is we're gonna try to add 2 points together, A and B. And the way we do it is first we draw a line through A and B, and the line at some point gonna find a third point. And when it does, we're gonna call that point minus A plus B, right? So we know when minus A plus B is, and we know what the negation operation is, so we know where A plus B is, right? It's just the mirrored point. Now, to give you a very simple explanation why it's drawing a line through those points, you can think about it it comes from the definition. It says A plus B plus C should equal 0, right? And from that definition, then they derive the equation. Now, it's interesting to note that for prime field, to find this point, you might kind of overflow the field, right? It might go because we have this modulo thing, right? And then the operation looks a little bit different, but it's the same operation, right? And this is the equation. This is the equations for the addition. So to calculate the position of point C, we use that equation, right? We calculate the slope between the 2 points, and then once we have a slope, we find the cross section. That kinds of from basic geometry, right? But now the geometry is done not on the real number but on prime fields, but because real numbers are fields and prime fields are fields, the mathematics is basically the same. Well, so for now, just trust me, that's a magical formula. And if you were to write this formula in Python, then the code would be pretty much the same as mathematics, just write in Python. There is one case, I stopped it on time. There is one case where there is no third point. If we draw a line through 2 points, there's gonna be no third point. In this case is when we add A to its negation, a point to its negation, because then it goes to infinity, and it will kind of, if it overflows, it'll go back to the same points. So for those points, for those situations, we say we add one more point to our elliptic curve, which is 41 points. We add 32nd point, and we call it point at infinity because it's kind of somewhere out there, right? What's important about point at infinity, it's gonna be our neutral element. So it's gonna be 0. Adding A to minus A equals 0. Makes sense, right? And adding any point to its negation is 0, so it's just 1, 0. And we have a group, because group needs to have neutral element, a 0. So that's important. Good, and here is, oh no. I propose I propose we get to second part of the presentation, then switch on lights, because now we have a little of those dark blue lines or dots. Once we're gone, let's turn off the lights so we can make some photos. Good. So a plus minus a equals 0, a plus 0 equals a, or 0 plus b equals b, or 0 or point of infinity. The point of infinity having this mathematical 0 notation that kind of resembles 0, right? So now we're updating our code to include those three cases. Okay, if you don't follow the code, that's fine. Just believe me for now that the magical equations are there. Good. So what's interesting about this? What's interesting about this is we can have a multiplication, but we're not multiplying two points together. We're just multiplying, we just keep adding point to itself, right? So we can say if 2a is just a plus a, 3a is a plus a plus a, and we can further deduce that, well, 1a is simply a, and 0a is what? Point at infinity, exactly, right. All right. So this is interesting because we can instead do something like this. Instead of keep on adding, we say we're gonna double a, and we're gonna double again, right? And doubling, if we keep doubling, it's gonna be, if we have a lot of additions, but instead we're gonna keep doubling it, it's gonna be much faster, right? So there is a thing called fast scalar multiplication, and there is a bunch of algorithms for that. I'm gonna show you the simplest, double and add. And double and add allows you to multiply, so this is a number on the top, and we're gonna multiply it by a point. And when we do, and we do it very simply, we just keep, here we're gonna iterate on bits, and for each we're gonna have just this temporary value, which we generate by keep duplicating the number, and we just add those where we have one in the position of binary representation. Does that make sense?
Why add?
Hmm?
Why add?
What do you mean add? Because you keep doubling and then you add those on those positions, right? There is many variants of this algorithm. There is side channel attacks, and it's not resistant to side channel attacks, and a lot of cryptography theory that says you should not use this algorithm in practice, but it's a good algorithm to use to explain, right? And yeah, we add it, and then we have, as a result, the number was 104, and we did 8 doublings in 3 additions to do 104 adding operations. In general, it's going to be logarithmic amount of doublings. So for 2 to the power of 256, which is the usual size we are interested in, it's going to be 256 doublings and up to the same amount of additions.
So
all right.
the naive way would be to just add. Right?
Come again?
We compare to the naive algorithm.
Yes.
Which is just adding.
Yes, which would be for 200 to the power of 56 would be more than atoms in the universe. So if you use all the atoms on Earth to build a computer and you would boil the oceans, it would be far from sufficient to calculate, right? Good. One last important piece of information about theory on elliptic curves is groups. So to generate a group, or subgroup if you will, because if we take the blue points are the group, then we're gonna generate a subgroup. So we're gonna pick a point G, we're gonna call it generator, and we're gonna keep adding, multiplying by subsequent numbers, or keep adding it to itself if you will, and this will generate a subset of points on the curve. What's interesting is at some point, as we're gonna keep adding it, keep adding G to itself again, it's gonna reach the point at infinity, right? I missed that. Yep, it's gonna hit the point at the infinity on the top, 14G in our case, and it's gonna restart the cycle at G and follow the same path. So we say the subgroup is cyclic, right? It's a subset of the numbers of all the points on the curve, and it's cyclic. And then we can pick another point, and what's gonna happen is we're gonna generate the same group or a subgroup. So it's gonna be another subgroup of a subgroup, but it ain't gonna use the points from outside the original subgroup, right? So that's interesting. And we are, of course, interested in big subgroups, as you will see in a moment. Good. So to summarize, we have negation, addition, doubling, and multiplying. 4 operations we can do on elliptic curve. Multiplying is fast and it's important. But there is one more operation we would be interested in, and this operation is calculate a logarithm. So imagine you multiply k by the generator. Can I retrieve the k? Can I, giving a point and another point on the curve, can I figure out how much time, what is the k, how much time do I need to multiply it, or by what number I need to multiply it to get the specific number? And the answer is these operations on big elliptic curves is not feasible. So you can say that in cryptography, operations you can do are as important as those you can't do. As far as we understand cryptography and group theory today, we cannot do efficient discrete logarithm. It's called discrete logarithm problem. Okay, but for that to happen, for us to be sure that discrete logarithm is difficult to calculate, infeasible if you will, we need to have a proper curve, a proper equation, proper prime field, and proper generator, right? So that would be a lot of mathematics to learn to figure that out, but we don't need to figure that out because we have cryptographic standards. And one popular standard is zkWarsaw, the one that is used by Bitcoin and Ethereum. Now, it has the equation we've seen before, and this is the order of P. As you see, it is a number pretty close to 256, as I already mentioned a few times, and it has a specific generator point defined by this long hexadecimal string, right? It's really big. It's really 32 hexadecimal nimbles, right? The 02 is actually a 02 is not actually the number. It's just comes from the encoding. Good. And yeah, so if you want to build something with cryptography, you just take one of those standards, and this standard seems to be very good for digital signatures as used by Ethereum, Schnorr Signature, and a bunch of others. And from the point we can calculate, or mathematicians can calculate the order of the group. Okay. And from the order of the group and the base point, we can calculate cofactor. So we can say how many so cofactor is the order of the group divided by the order of the subgroup, right? So if you have cofactor 1, that basically means that every single point on the curve belongs to the group we're talking about. And that's the case for SECP256K1, which makes it friendly for calculating digital signature. But there are other curves with other properties, with other cofactors that are like, for example, 8. And there is this other curve that is called, well, let's see how it's called. 255.19, I believe.
So why is it good?
Well, we'll see in a moment. So this is just to give you an example of another curve. This is curve 255.19. And this is used for Diffie-Hellman key exchange. So when you're connecting to your bank and there is a green lock in your URL bar, you're probably using this one. And yeah, it has different order, different generator point, and it has cofactor of 8, which means only every 8th point on the curve belongs to the group that you're using for your cryptography. Good?
What does it mean for us, the cofactor 8?
I mean, for us in Ethereum, nothing specific, I guess.
As a user.
Well, it just means that your different properties. I mean, you're gonna see why h equals 1 is interesting. And for example, in pairing groups used for BLS signatures, that's much more complicated and that has a bigger implications, right? So what is Ethereum wallet? Well, Ethereum wallet is private key and address, right? So what is, now finally after we went through all those mathematics, we can talk about Ethereum, right? So I think we can turn off the lights, yes. So, too fast. Go back. Good, all right. So private key is just a number, and it's a number called scalar. So scalar is anywhere between 0 and n-1. So it's modular arithmetic, but not modulo p. It's not a prime field now, but it's a modular arithmetic modulo size of the group. Everybody's eyes are still adjusting. Should I repeat? Okay, right? So prime field is just a random number, okay? Now the question is, and we just randomly picked 11, right? Play, no, doesn't work.
It's not 11.
Well, it's 11 hexadecimal, so it's 17, right? Great catch. So that's a private key in our example, and we're gonna calculate the address. To calculate the address on Ethereum, what we need to do is we need to first calculate, is it going? Oh yeah, finally. Where is it? Feels like I need to do it manually. We're gonna calculate a public key. And public key is nothing else but our number times the generator, right? So it's a point on an elliptic curve. Okay, let it sink. Public key is a point on an elliptic curve. Good. I feel I need to, yeah. Good. Right? So we remember groups and 17G, we just picked that number, right? We had the chart before. Okay, this is our public key. Okay? And you can sense the intuition. It's easy to generate random private key. Having a private key, it's easy to generate a public key. But once I have a public key, it's not easy to go back to the private key. Good. Now, public key is not the same as address, because address is to generate an address, we need to take a public key and we need to hash it together. In case of Ethereum, it's Kajak 256 that we use to hash. And then we have a hexadecimal result, and from that we truncate and we use, I think it's last 20 bytes, right, Arek? Last 20 bytes, yes. So 40 hexadecimal nimbles, right? And don't forget about the iconic, here we go, 0x at the beginning. Don't forget about 0x, you know, otherwise it's not an Ethereum address. Good. So this is it. In the video, I'm also doing, so for some reason video is not collaborating with me and I cannot put it on play, so I kind of scroll it. But of course, we randomize a big prime number modulo, a very big, not prime number, but we randomize a very big number, right? Truly random number, modulo order of the group, which is close to 256, right? Good. I think we can close it now and go to the second video now. Good. Any questions? Good. So that was introduction. If you felt lost at any point, feel free to watch zkMarek channel. Good. This is the logo. Yeah.
So if we hash the public key to get the address, how do we run operations? Like if the public key is not known.
You don't.
Okay, so we just...
It's just an address. It's just an address now. It's not reversible, right? You cannot go back from address to the public key, which is a good thing which is a good observation. This is gonna be this is gonna be important detail in the implementation. Okay, so digital signature algorithm. So digital signature algorithm. This is an algorithm used in Ethereum and Bitcoin and several other places. And if you were to think about it from the very theoretical standpoint, it's basically three functions. A first function that generates a key pair, secret key and public key. Secret key, private key, it's both terms are used to name the same thing. There's a sign function, and the sign function takes a message and a secret key and produces a signature. A signature can be used to verify, using verify function, that message, signature, and public key, that message was signed by signatory, by the guy who owns a private key, right? And we do it by passing those three arguments: message, signature, public key, and it's a boolean, true or false. True if it works, false if it doesn't, right? True if signature was created from the specific message with a secret key, right? But as Orest noted, that's not very useful in Ethereum because we don't have a public key in Ethereum, right? Therefore, actually, Ethereum and Bitcoin before that used another version of the algorithm that name is not verified but recover. And that algorithm takes message and signatures and return public key. When it does, we can do the same operation to the public key to generate an address, right? So that's easy peasy. Okay.
How does it recover?
What do you mean?
How can it get to...
That's gonna be on the next slide. Okay, and if you look at the source code, because it's using elliptic curve, so actually digital signature algorithm works on different groups, not only on elliptic curve. So oftentimes we use in the code you can see EC prefix which stands for elliptic curves. Hence you might already Solidity developers EC recover, that already might rings a bell, right? And the last thing we're gonna do before getting into details is we're gonna think about typing, right? So generate key pair, already we know what it generates, right? A secret key that is a scalar and a public key that is elliptic curve point, right? What ECSign takes is a message. Now message is usually a string of bytes, but for the purpose of our cryptography, we're gonna hash it and we're gonna treat hash as a scalar. And a secret key that's gonna be a scalar, and it produces a signature that is 2 elements, R and S. Now Ethereum signature has this additional V element that we're gonna talk about in a moment. But R and S are usually scalars, or as you see in a moment, actually in Schnorr signature, R is a point. And you know, that keeps going. Messages, if you want to verify, message is a scalar, signature is R and S and maybe V, which are scalars, and public key is EC point, or we can do EC recover and basically move this argument to the result. Easy?
Point being the Y?
X and Y. X and Y. It's a point. It has X and Y. Yeah. There are clever ways to compress it. All right. So now we are finally getting to the essence of it. We're gonna play the game of digital signature algorithm. The game gonna have 2 players: signatory, the one who's gonna sign things, and verify, the one who's gonna verify if the signature was indeed used. But the signature was indeed generated by signatory on a specific message. So we're gonna have a signatory. The red part is private. He has a private key, he has a public key, he has a message, and what he's gonna do is he's gonna create a signature. Well, we already know what the private and public keys are, right? So the private key is just a random number, a scalar. A public key is a point, a private key multiplied by generator. Well, and the message is a string of bytes, but we're gonna hash it to make it a scalar as well. Now, one thing to note when talking about hashing to make a scalar is that, yeah, go for it. Yeah, is that's gonna generate a number between 0 and 2 to the power of 256, while scalar is somewhere between 0 and a big prime field close to 2 to the 100 of 256. So we need to somehow handle this edge case. If we are in between the prime number and 2 to the power of 256, then we do modulo or something. It doesn't matter that much. The probability of randomly picking that number is so low that you can just reject those cases. Okay. So to generate a signature, we're gonna generate a new secret number. It's gonna be yet another scalar, yet another random number, and we're gonna generate R, which is just a secret number times G. So it's kind of deja vu from generating a private key. Random. No, random is random. Random is truly number. It's like just something. I don't think you can generate signatures on-chain. You need to do it off-chain. And I could do another hour-long presentation on randomness on-chain, but it's kind of hard if possible. I think we could go to really exotic edge case discussions to get the idea if randomness on-chain is possible, but in general, you don't need it, right? You just generate off-chain, right? Because you sign off-chain, you can write a smart contract that signs something. There is theoretically, cryptographically possible to create a smart contract that could sign something. What's the name of it? In Fishes, something of oscillation, and they ran a hash function, and it took 1 year to run a hash function with this cryptographic proof. So okay, this is completely side topic. Doesn't matter. Good. So we're almost done with our digital signature algorithm, but we're gonna do two things. First thing we're gonna do is we're gonna say, okay, so from this point R, we're just gonna take Rx. Right, so we're gonna just take the x coordinate, and we're gonna take it modulo n, which, as we know, is different than the p. Right, so x on the x-axis might be anywhere between 0 and p, and we know that n might be smaller. So it's modulo n. And here is an interesting thing to note: in SCP-256K1, where cofactor is 1, those numbers are really close. So the probability of hitting number that is bigger than n is really, really low, and you can basically skip that. You can basically assert, you still want to make sure your algorithm works properly, so someone doesn't use that as a vector of attack, but you can just crash your program because it's never gonna happen probabilistically.
What's n? It's the order of the field?
The order of the group. N is the order of the group. P is the order of the field. No. It's close. In case of SCP-251, it's close because cofactor is 1. If cofactor was 8, it would be 8 times smaller, right? Well, it's just the property of mathematics that if you have a elliptic curve defined on the prime field, it happens, it's mathemagic, that they're gonna be close. And there is a mathematical the property that says it's going to be, I believe Arek can help me out here, I think it's not further away from each other than a square root of n, right? So which is, by the way, very close if you think about it, because probability of hitting randomly something of square root of n is like, less than hitting a random particle from the universe or something, right? For cofactor 8, it's much further away because imagine for 41, in our example, in the chart, there was 41 on the prime field and 42 on the group. And because cofactor was 1, that says every single point in the curve belonged to the group, which means 31, 32, that's pretty close. But if the cofactor was 8, then the group size would be 42 divided by 8, which would be 5-ish, right? Right? So then it would be 5 and 41, right? Good. Those are, took me months to figure out all these details. It's like, I really hope you can do it faster than I did. Okay, so this is the digital signature. Digital signature is just a pair, R and S, and R is just another representation of the point R, and S is this weird equation. You can think about obfusculating secret, private key, message, and R, like putting it all into one mixture, like mixing colors into something that you cannot really, because of the discrete logarithm problem, you cannot kind of put it back, you cannot deassemble it into pieces, right? So it becomes just some random number that doesn't make any sense if you don't. I see someone is making photos, it's all on YouTube. Well, this part is not on YouTube, so.
The bit with appending randomness to the message, is this to prevent people from...
Yeah, you can think about the secret and error, like the new pair that we're adding, as this obfuscation mechanism, right? We're gonna, like this random color you mix with other colors that you don't know how to, but we're gonna show you.
You add this thing so that it's harder for an adversary to reuse the same message over and over again? Is that why?
The random, are you asking?
The randomness when creating the signature.
Well, we just need a pair. We just need a pair of secret and a secret and a public, and that kind of goes one way, but is not reversible, right?
So you could just multiply by your private, the message.
Stay tuned for answer to this question. So come again?
Every time it's a signature you generate it, will you generate a new random secret?
Every time signature generated, yes. Okay, but stay tuned. There is a start to that. There is a footnote. We're gonna go back to that.
It's not deterministic. The same message will have...
Exactly. So signing 2 times and not deterministic, right? You have 2 different signatures from the same private key and from the same message, which might be a desired or not desired property depending on your context, right? Okay. Now, as we defined what the signature is, we can jump to verifier, and we're gonna find out how to verify the signature in DSA, in digital signature, or ECDSA, elliptic curve digital signature algorithm. All right, any second now. Boom. Okay. So what verifier has? Well, verifier has a public key, message, and a signature. And to verify, he's gonna try to retrieve R from the small r, right? But there are only 2 options, as you remember probably. And then what we're gonna do next is we're gonna just calculate those 2 auxiliary numbers, right? Maybe I'll try for that thing to disappear. And from those 2 auxiliary numbers, we're gonna calculate Q, which is U1 times G plus U2 times R. And okay, for now it's just a bunch of, equations, but as you will see in a moment, if Q equals public key, then we calculate Q. So this is the result of our EC recover. If Q equals public key, then the signature checks. Okay. How come, you ask? Well, let's see. What we're gonna do is we're gonna keep substituting all the different numbers. We're gonna start with R, which is just a secret times G. Then we're gonna extract G in front of the bracket. Then we're gonna substitute U1, and we're gonna substitute U2, right? And then we can see, we can substitute S as well. And you can see secret and secret to -1 gonna cancel each other out. Yeah, we remember this is all prime fields. -1 is this magical inversion operation we didn't talk about. And then you can see R-1 gonna cancel each other out. And so the message gonna retain, remove the brackets, message times R-1 cancel each other out. Boom, we're at the public key suddenly, right? So what happened, a quick intuition about what happened, we kind of obfuscated all of that, but in a way that we can retrieve that if we have proper information, right? If we have public key and a message and a signature. Oh, so that's where the magic happens. And it's important also, hey, we cannot do it, we cannot manipulate it. We cannot, without private key, the math wouldn't work. Without the proper secret and R pair, it wouldn't work, right? So that's pretty cool. So this is, my good friends, this is digital signature algorithm as used by Bitcoin and Ethereum. Now, the question that came a few times was about determinism, right? So we use the secret that we say is random. If you look at the implementation, the secret usually, or white papers, the secret usually is designated as key. So in our case, k is a random scalar. Now this is not good for Bitcoin or Ethereum because, well, you sign every single transaction. And when you sign a transaction, you would like it always to have the same hash. And the reason is to be able to easily say, is this transaction the same as this transaction, right? So if there is non-determinism, it kind of becomes difficult to compare. This whole notion of, is it the same transaction becomes non-trivial, right? Which is definitely not what we want because it makes DApp implementations harder and so on and so forth, right? So we want deterministic transaction, and as Ores already was kind of guessing towards the right direction, is we can do it, and this is gonna be gross oversimplification, and every cryptographer gonna tell you this is not true because I'm gonna use hashes here, but what you really use is hmax. If you know what it is, you know what it is. If you don't, we're just gonna oversimplify here and say we're using hashes, and we just hash secret key plus hash of concatenation of secret key and hash of the message, right? So we need both of them, otherwise, well, the random number would be the same if we just hash secret key. By the way, if you sign something with the same random number, there is an attack that can retain the secret key, the private key from two signatures. So you better not do that. Good. Yeah, there is an attack. I believe from 2, maybe from more, but I believe from 2. Okay, there is one other interesting mathematical property. Actually, if you use R and S, then both S. Did I do something again? The battery seems to be fine. No escaping me. Okay, so technically from purely mathematical reasons, both S and n minus S are proper signatures, although you need to flip R, right? So it will big R, the Rx, the small, the X coordinate is the same, but it's a different of the 2 points, right? So hence S and n minus S are proper signatures. So in Ethereum, to make sure there is only one proper hash, we say S needs to be smaller than N, which simply means when we sign a transaction, we need to check if S is smaller or equal N divided by 2. Yeah. N divided by 2, right? So if it's in the upper half, it needs to be in the lower half, right? Of the prime field or group. Is it N or P? Who knows? and because because S is a scalar. Good, right? Does that make sense? Should I repeat it? I think it checks out, right? So S and N minus S are proper signatures. You might need to flip the R point for that, or negate to be mathematically correct. But so for that reason, Ethereum requires your S to be smaller than N divided by 2. There is a missing division by 2 here.
So how does this avoid the attack?
Well, because then you would
It's going to be the same for the same message. Like that's the feature, right?
just to make sure you're deterministic.
Yeah.
If you wouldn't have this last condition, then there will be technically 2 proper signatures.
Yeah. But how does it deter the attack when you recover the private key from 2 signatures?
Well, I don't know if there is an attack in a sense that transaction needs to have different nonces and so on, right? So there is no per se an attack, but it just makes it so there is a very precise definition of of equality of transactions, which is what you want to do. You don't want to check if transaction is correctly designed and then figure out that the other one was actually, there is another one that was actually proper, right? From even when building, front end or something, right? Or infrastructure. Yeah, does that make sense? Good, and I think my slides are off, so I'm gonna jump forward and then I'm gonna jump backwards. No, not here yet. What was the other? Deterministic. And there was EC recover. Give me a moment to. Pretty sure there was something to jump to. No, okay. I can't find it, so we keep going. Good. Or not. Well, okay. So here is EC recover function solidity. It takes bytes 32 hash. It takes V, R, and S. So we talk a lot about R and S. Now your job is to figure out what V does. RS and AREC, you're not allowed to answer, right? So we talk about what RS and SS, and like those are 32 bytes. Big numbers. As you know, there are a scalar, so modulo group order. Now, why the hell do we have a V here, right? And here is the fun part. Yeah, now I remember. I'm gonna show you another slide now. Okay, and this is Ethereum transaction, by the way. So there are two ways to use EC recover. In Solidity, there is a function, and every time you sign a transaction, you basically use a DSA, right? So you have all those values in Ethereum transaction from 2 value nouns to avoid replay attacks, right? Chain ID, hash of the transaction, and then you have those 3 fields, S, R, and V, right? And S and R we talk about. Now V have one of the 4 values, 0, 1, 27, 28. Why? Any ideas? What does V do and why does it have such a weird set of values? Anyone? Why 4 values? And why 27? Good. So, any ideas? Anyone? Like, any direction why you need? No? No? Okay. Good. Good. Let's try to move it forward then a little bit. And so I think I have the next slide, but it's just not coming. So we go back to the elliptic curve, right? So R is the x coordinate, but we don't know what the y coordinate is. But there are only two possible coordinates, right? So why not use 0 and 1 to say, okay, this is the one or the second one? Well, 0 and 1 happen to be easy to confuse. So one of the Bitcoin developers used 2728, and it's still used today. It was derived by Ethereum because, you know, if you set it's easy to accidentally set V to 0. It's not that easy to accidentally set it to 27. Interesting thing is that if you would use, so Bitcoin was still supporting, I believe Bitcoin was still supporting the edge case where you randomly picked the number between n and p. So I believe they actually used 0, 1, 27, 28, and 27, 28 was for the common case and 0, 1 for the extreme case. I'm not absolutely sure, but it's important to note that if we use DSA on a different elliptic curve with another cofactor, that could be, for example, 16 values, right, if the cofactor was 8. Good. And I think that was, now we need to jump. Now I'm gonna show you the implementation and you're gonna see.
Wait, it would be 8 values.
Yeah?
Because it means that the field, no, sorry, which one's smaller?
Field is always bigger.
But then you would not have 8 possible values.
No, because you do modulo. You do modulo, right? So it could be here, 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 and here. And when you do modulo, they all land here, right? So it could be here, 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 right? Does that make sense? Is that visual representation sufficient? Okay. So this is the implementation of Zine done by Arek, who's sitting here. So shout out to Arek. Woo! So as you see, it's just a few lines of code. What's the big deal, right? So what we do first is we kind of take we calculate R from the public part of it, from the big R, right? Yeah. Important detail: K here is passed as an argument, right? So this is the random number, let's say, right? And we calculate S. We calculate V, which is just the odd, which we just say if it's, you know, odd or even, oddity of the number, and then we need to flip S, right? If S is bigger than N, right? And that's it. That's the whole signature. Why there is so much code? There is like serialization, deserialization, standard edge cases, but the heart of design is really simple, just a few lines of code. And it's not very different for EC recover. You take the Z, which is in this case representing the message that is already converted to a field, to a scalar, sorry, R, S, and V. And yeah, basically we recovered the R from big R from small r and V. And then we just calculate U1, U2, and Q, and return the Q, which is a public key. In case of easy recovery and solidity, we also need to convert the public key to the address, right? Again, just a few lines of code. Good, questions? Good. If no questions, then okay, we talk about this. Good. So now we can talk about the trick. Almost ready. We need to explain the Schnorr signatures first. On the left side, everything we've done so far, this is SCDSA, nothing new happened here. So first thing to note is Schnorr is using the same cryptographic standard, SECP 256 K1. It also uses private and public key. It's the same way of generating. And it's also gonna use secret, and it's also gonna use R, which is like a multiplication of generated times secret, right? So you can see already there is a lot of similarities, but this is where the similarities kind of end, because as you see, we pre-process message, and actually we don't hash the message itself, but are concatenated with message, right? So this is the first important difference, that R is now part of the message, of the hash of the message. But thanks to that, S is much simpler. It's simply secret plus private key times message. And as you will see in a moment, actually Schnorr's signature is much simpler than DSA. And there is a good reason for that. Mr. Schnorr invented his signature and he patented it. So you would need to pay to use it. So the US government body that was in charge of standardizing signatures, cryptographic primitives, came up with ECDSA, which is very similar, just a little bit more complicated because they couldn't use that. And actually, Schnorr has this interesting property I'm going to talk about in a moment.
So the patent expired now?
Patent expired in 2009, I believe, just 2 years after Bitcoin. So Satoshi would probably use Schnorr, and now they implemented Schnorr in Taproot in the recent Bitcoin fork, right? So now Schnorr is in Bitcoin. So, yeah. And, yeah. And, okay, and, well, it's simpler, as you're gonna see, but there is another interesting property I'm gonna talk about in a moment. But here is just a reminder, this is how we verify ECDSA signature. This is how we verify Schnorr signature, and you can already see it's kind of simpler. You can address should be not here, so don't think about the address, because what we do is we kind of just recalculate the hash of the message, right? And we just calculate this auxiliary, just one auxiliary number instead of 3, which is G times S minus public key times hashed, pre-hashed message, pre-processed message, right? And we're gonna answer one simple question. Does this newly calculated number equals to the R, to the public part of the signature, right? So as you see, R is a number, is a point now, so the signature now is not two scalars, but a scalar and a point, right? So why is that? Well, you can kind of do a substitution here, and you're gonna see everything cancels each other out, and you have an error. I don't have an animation for that, but you can see S is secret plus private key times message, right? And public key is just G times private key, times private key. So you can extract G in front of the bracket, and what you're gonna have on the right side is minus private key times message, which you can also see is on the top, right? So so that's gonna cancel each other out, and what you're gonna be left with is G times secret, which is basically R, right? So if you don't believe me, take it as a homework. Gonna take you like 5 minutes to calculate, maybe less. Good. And now comes the trick. So EC recover, by the way, is 3,000 gas, which is really, really low. The basic transaction on Ethereum is 21,000, and if it's ERC20 transactions and it needs to write a slot, it's like anywhere between 10 and 30,000. So it's like if 3,000 is really, really cheap. So, and if you would like to naively verify signature, that's going to be hundreds of thousands of gas, if not a million. But you can construct a zk proof, it's still going to be 400,000 gas versus 3,000, right? So you can see the gain is huge. So what we're going to do is we're going to do a trick. We're going to calculate just some new things, just new variables, right? Just bear with me. We're going to calculate this message prime. Again, you can ignore the address, which is going to be R concatenated with the message, and we're going to calculate 3 values. Message, which is minus S times public key, but not the whole public key, just the X coordinate. And we're going to calculate R. Well, R is just a public. Again, it's the same variable. It's the X coordinate of the public key. And then you have an S, which is minus message, well, process message times, again, the X coordinate of the public key. And I'm going to convince you in a moment that if we supply those to the EC recover function, we're going to, in result, at the end, instead of public key, we're going to get R, right? This R, this R, this R, right?
So what makes Schnorr so expensive in the name? Is it the hashing? We hash in both ways, in both scenarios. Why is it such a problem in the first?
I'm not sure, to be honest. Maybe I exaggerated. Maybe it's not that expensive. I'm not sure, to be honest. Modular arithmetic.
The hashing, of course, happens off-chain, right? The hashing to the message, like we don't.
I'm not sure. Maybe I exaggerated, actually. I know that some other signatures are expensive, but they are using different elliptic curve. So I'm not sure. Maybe I exaggerated, but I'm pretty sure it's quite expensive. Like order of magnitude, easily. Okay. Good question. Okay. So what we're going to do is we're going to substitute. Okay. So to get from that to here, we just substituted message RNS, and you can instantly see a lot of things going to cancel each other out. This is going to cancel each other out. This is going to cancel each other out. So don't have such a nice animation for that. And we're going to substitute that again, right? So now that we have U1 and S1, we're going to substitute that. We're going to substitute that, and we're going to substitute R as well. And we ain't gonna care about the Q, we don't gonna care about that. What we're gonna care if it equals R prime or R, right? So this is after substitution. S times G plus minus message prime, preprocess message, times public key, does it equal R? Well, let's see what R is. G times S minus public key times message prime. Same thing. Hence, we can do, and this is the actual code, you can just calculate with a little bit mathematical preprocessing, you can actually just use EC recover to recover the R from the Schnorr signature.
So what's the precursor? What does it do?
Well, it's just calculating those auxiliary numbers we've seen in the previous slide. You're just calculating R and S, well, and preprocessed message, just those three numbers. And I didn't really study the code. I took it from the repository, so I'm not guaranteeing it works, but yeah, this is the group order on the top. So we're doing mul mod. So those are operations on the scalars, right? This is why, because we're using multiplication modulo Q. Good. So that's the trick. Trick was pretty easy versus the understanding everything all the way to the trick is tricky. Good. I think it's worth mentioning that I didn't came up with this idea. There is Not who kind of came up with this idea, and it's evolution of idea that Vitalik have had and shared on the Ethereum research forum, and there is a implementation there. Good. And if you want to watch more of those kind of things, that you can go to YouTube at zkMarek. Any questions?
I want to ask only one question. The tree, does it work in any production environment?
Pretty much, I believe so, yeah. There is a wallet. So the way I learned about the trick, I went to a presentation and there was a wallet using Schnorr signatures. And the cool thing about Schnorr signatures, I didn't always ask about, but I didn't answer the question yet. The cool thing is what you can do is you can fairly easily do signature 2 out of 2. So you can have 2 signatures and verify with one EC recover. And the reason is, if people have multiple secrets, let's say I and Orest, we both want to sign a transaction, what we can do is we can both generate a secret and we can just hash those 2 secrets together in the message, right? And that way we can easily combine 2 out of 2. I don't believe you can do 2 out of 3, which was my initial understanding what you can do with Schnorr signatures. But I don't think you can do it, but if I'm wrong, someone can tell me how to do that. Yeah, but that's pretty cool property. And this particular wallet allows you to do like one start transaction on one device and kind of verify transaction with the second device. And they mentioned they're using this trick, and I'm like, well, I need to know how it works, and it kind of led me to investigate and doing this presentation. In general, verifying signatures is a big thing on Ethereum and other chains. And Ethereum, well, there is a standard, 256K1 is a standard used by Bitcoin. It was picked by Satoshi Nakamoto because the one that was pushed by the government body, I think it's called NIST, I think it's the name of the government body, was suspected of having backdoors, mathematical backdoors. So they now using, so they decided to use another variant, another curve that didn't have these properties. They didn't have this shadow over it. So therefore, the whole world is using the standard, while Bitcoin and Ethereum is using something else. And the sad thing about it is, if you want to sign your transaction with Face ID or Touch ID or, web outing, like all those things that get standardized in the browser on the devices on Android, on iPhone, they all use P256. So there is like a whole thing and race and discussion. Should we enable different signatures? Why should we have 5 different signatures? Should be one general API on Ethereum that allows you to do different signatures and so on and so forth. And yeah, there is a wallet, and I don't know how they do that, and very few people know how to do that, but maybe next presentation, that is able to do SECP256 R1, which is the one used by iPhone, the one used by the web outing, in 70,000 gas, roughly, 70,000, right? So it's still 20 times more expensive, but 70,000 is still like the cost of similar to the cost of the token transaction, right? So it's like it doubles the cost of your token transaction. It's bearable, right? Which is still not 10 times of your token transaction, which is for more naive implementations, right? So it's like signatures is a huge topic. It's not just a theoretical thing. People looking for those hacks, people discuss if we should implement more signatures on chain and so on and so forth, right? And it's a huge impact on usability and what is possible to do on the wallet side. Any other questions? Come again? Hopefully, I don't know.
This one is out already. You mean from last month?
I mean, this Schnorr.
Soon TM. Soon TM. As soon as we have some time, which is not easy these days.
Until then you can oh, you mean your video?
And the Schnorr video, right? The elliptic curves video is out, but the digital signature and Schnorr is digital signature algorithm and Schnorr is not. Hopefully soon. I really want to. You see, it's already kind of halfway done, so good. There's much more to explore in cryptography. There's many more videos I would like to do. Questions? Do we have a pizza or something? Is it waiting or is it coming? Oh, it's waiting. Now you're telling me? All right, thank you very much.